Good day, my dear grade 12 students. Welcome to your school on the air in physical science. I hope you are safe and well amidst the pandemic. I'm glad to be with you today on this journey as you will discover new lessons via radio and television. I am Christian Tiraneses from CCNHS Cabor 1 Extension, SDO Cagayan City. Before we begin, make sure to grab your module as well as your activity sheet for this lesson. Please stay tuned to DWND-FM and CMD Cable Channel 11. This video is also streamed live at SDO Cagayan City Facebook page. Now, as we move on to our subject to learn new things while staying at home and preparing for our lesson for today, I want you to pay close attention, listen carefully, and learn thoroughly. If you're ready, let's get started. In the previous lesson, we looked at the structure and properties of molecules to determine their polarity. Are you able to remember them? Let's do a fast analysis by answering the following multiple choice questions. Okay, are you all done? Here are the answers. Now that you know how to determine the polarity of molecules based on their structure and properties, let's talk about our topic for today, which is all about the general types of intermolecular forces and their effects on the properties of substances. At the end of the lesson, you are expected to describe the general types of intermolecular forces as well as explain the effects of intermolecular forces on the properties of substances. Intermolecular forces are attractive forces that act between molecules or atoms of pure substances. Powerful molecular forces, such as covalent and ionic bonds, tie atoms together in molecules. Other types of attractive forces, on the other hand, are present to hold these molecules together, resulting in various states of matter with their own bulk properties, such as boiling point, freezing point, and melting points, and viscosity, among others. The three general types of intermolecular forces are van der Waals forces, ion-dipole interaction, and hydrogen bonding. Van der Waals forces, named after physicist Johannes van der Waals in the year 1837 to 1923, under this category are the following: dipole-dipole interaction, dipole-induced dipole interaction, and dispersion forces or London dispersion. Under the van der Waals forces, let's discuss about the dipole-dipole interactions, which are the attractive forces that act between polar molecules. Diatomic molecules made up of elements with significantly different electronegativities like HCl or hydrogen chloride have partial charges, positive at one end and negative at the other end. This is due to the unequal distribution of electron density between the atoms of diatomic molecule. The magnitude of the attractive forces depends upon the magnitude of the dipole. The partial positive charge on one molecule gets attracted to the partial negative charge of another molecule in the vicinity. The larger the charges of the dipoles, the greater the attractive forces between them. Certain physical properties of the substance reflect the magnitude of the dipole-dipole interactions. An example of this property is boiling point. Substances with large intermolecular forces of attraction between one another are expected to have a higher boiling point. The dipole-induced dipole interaction, just like dipole-dipole forces, depends on the presence of polar molecules. The other molecule needs not be a polar one. The partial charges present in the dipole cause the polarization or distortion of the electron distribution of the other molecule. This gives rise to regions of partial positive and negative poles. This induced dipole will then be attracted to the original polar molecules, resulting to dipole-induced dipole interaction. Dispersion forces or London dispersion forces, named after the German physicist Fritz London in the year 1900 to 1954. Under the correct conditions of pressure and temperature, non-polar gases like oxygen and nitrogen can be liquefied. This means that there are attractive forces between the molecules of non-polar molecules. These intermolecular forces arise from the movement of electrons in the non-polar molecules. The distribution of electron density in non-polar molecules is symmetrical and uniform. Since electrons in any molecule have the freedom to move about within the molecule, there are moments when there is non-uniform electron density distribution within the molecule, which gives it a temporary dipole, called instantaneous dipole or temporary dipole. Look at the illustration. This will eventually induce dipole in the neighboring molecules. Dispersion forces act not only between nonpolar molecules, but also between all molecules. Dispersion forces are the only intermolecular force exhibited by nonpolar molecules. To better understand this lesson, please watch this video.
Electrons in an atom are in constant motion, but at some point in time there are more electrons on one side, creating delta negative and delta positive charges, or an instantaneous dipole. The instantaneous dipole on one atom can induce an instantaneous dipole on another atom, and they are oriented to cause an attractive force. Later, the electrons on both atoms have moved, but they tend to move together to preserve the attractive force.
Okay, let's move to ion-dipole interaction, which is the attraction between ionic and polar molecules. When ionic and polar substances are fixed together, such as dissolving sodium chloride in water to form an aqueous solution, they exhibit an ion-dipole interaction between them. The magnitude of the ion-dipole interaction depends on the charge and size of the ions, the dipole moment, and size of the polar molecule.
Dissolution of sodium chloride in water.
First of all, let's have a look at the properties of water. In a water molecule, the oxygen atom is more electronegative than the hydrogen atoms. This leads to a partial positive charge on the hydrogen atoms and a partial negative charge on the oxygen atom. Hence, water is a polar substance. When a crystal of sodium chloride is added to water, positively charged sodium ions are attracted by the negative end of water molecules. Negatively charged chloride ions are attracted by the positive end of water molecules. These attractive forces can overcome the ionic bonds between oppositely charged ions. Ions are then pulled away from the lattice. Therefore, sodium chloride is soluble in water.
Okay, let's move to hydrogen bonding, which is a special type of dipole-dipole interaction. Dipole-dipole interaction occurs between any polar molecules. On the other hand, hydrogen bonding occurs only in molecules that contain H-bonded or hydrogen bonded to a small highly negative atom such as fluorine, oxygen, and nitrogen. An atom such as fluorine draws the electrons towards itself because of a high electronegativity, which means that electron density is drawn away from hydrogen. This gives hydrogen very high partial positive charge, since hydrogen has only one electron, which makes it practically unshielded. The large partial positive charge of the hydrogen end of the molecule becomes very much strong dipole-dipole attraction between the molecules. Let's have an activity that will help you recall what you understood about the types of intermolecular forces present in each substance before jumping into our next topic. Now that you understood about the types of intermolecular forces, let's discuss our next lesson, which is all about the effects of intermolecular forces on properties of a substance. The properties of substances as viewed on the macroscopic level can be explained by the types of intermolecular forces present between and among substances. These bulk properties can be predicted through an analysis of the interplay of intermolecular forces in each substance. The chart tells us of the relative strengths of intermolecular forces. This can be referred to when trying to relate the IMF or intermolecular forces to the properties of substances. Notice the chart, okay? And London dispersion forces is the weakest, while ion dipole is the strongest. Okay, let's move to the properties of substances affected by the intermolecular forces. Number 1 is the surface tension, which is the amount of energy required to stretch the surface area of liquids. An example of surface tension is capillary action. It is the ability of the liquid molecules to move against gravity. The forces bringing about capillary actions are cohesion and adhesion. Cohesion is the intermolecular forces between like molecules, while adhesion is the attraction between unlike molecules. If cohesion is greater than adhesion, there is a depression or lowering, resulting to a lower height of the liquid in the capillary tube. The stronger the intermolecular forces possessed by molecules, the higher are the surface tension of the substance. To better understand surface tension, let's watch this video again.
Surface tension occurs because molecules of a liquid attract one another. The attractive force between similar molecules is called cohesive force. Cohesive forces inside the liquid are cancelled out, so interior molecules have a low energy state. However, boundary molecules have a high energy state, as cohesive forces are not cancelled out on the surface of the liquid. Consequently, in accordance with the principle of minimum energy, the boundary molecules are pulled constantly towards the inside of the liquid. As a result, it attempts to obtain the smallest surface area possible. This is why a free-falling water droplet takes the shape of a sphere. The phenomenon of surface tension becomes more complex when molecules of a solid surface interact with the liquid. The attractive force between the molecules of a solid surface and those of a liquid is called adhesive force. Wetting is a characteristic ability of a particular liquid-solid pair which depends on the magnitude of the adhesive force and the cohesive force between the molecules of a liquid. If this force is strong enough, the liquid spreads on the solid surface. In other words, it is capable of wetting it. However, if the adhesive force is weak, the liquid in contact with the solid surface can reduce its own surface area, and no wetting occurs. Mercury, for instance, is a non-wetting liquid. The wetting ability of liquids determines how they behave in thin tubes, that is, capillaries. The law of communicating vessels does not apply to liquids in capillary tubes, meaning that the liquid is not on the same level in these tubes. Instead, capillary action can be observed. A capillary containing water exhibits capillary rise, while a capillary containing mercury exhibits capillary fall. Capillary rise occurs when the liquid wets the wall of the tube, that is, when the adhesive forces between the tube and the liquid are stronger than the cohesive forces between the water molecules. If it is the other way round, capillary fall happens. Surface tension and capillary action play an important role in nature. For example, pond skaters could not run on the surface of the water without the presence of surface tension. The legs of these aquatic insects are covered with tiny hairs, which provide a small surface area, thus making them non-wettable. Due to the surface tension, the surface of the water acts like a membrane that can support the weight of pond skaters, and tiny depressions form on the water under their legs. They can launch themselves from these depressions, reaching speeds of up to 90 centimeters per second.
Let's move to number 2, which is viscosity. It is the amount or the measure of a liquid's resistance to flow. The greater the viscosity of a liquid, the more slowly it flows. The viscosity of substances decreases with high temperature. Thus, syrup flows faster when hot. The strength of intermolecular forces affects the ease with which substances flow. Liquids that have high intermolecular forces are highly viscous. The presence of strong hydrogen bonds or H bonds in some liquids makes these substances highly viscous. Let's watch another video about this.
Sugar, oh honey, honey, you are my candy girl, and you got me wanting you, honey, oh sugar, sugar, you are my candy girl, and you got me wanting you. I just can't believe the loveliness of
The LEDs, or the Lewis electron dot structure of glycerol, shows 3 OH or oxygen-hydrogen groups that can participate in hydrogen bonding, whereas water has only one OH group or oxygen-hydrogen group to form H bonding. Glycerol is more viscous than water. Let's move to number 3, which is boiling point. Depends on the equilibrium vapor pressure exerted to the liquid or solid above liquid or solid.
When a liquid changes into a gas gradually, like a puddle drying on a warm day, it's called evaporation. When it happens more rapidly like this, we say the liquid is boiling. The particles in a liquid tumble over each other, heat it up, and eventually the particles have enough energy to escape. The liquid breaks up and becomes a gas. In a gas, the particles move as far away as possible from each other. Gases take up far more space than a liquid. In fact, 1 litre of liquid water expands to fill 1,700 litres as a gas. So, what makes popcorn pop? Tiny amounts of liquid water trapped in each kernel suddenly expand. It changes from a liquid to a gas and makes the corn explode. A thermometer in a beaker of vigorously boiling water reaches 100 degrees Celsius. This temperature is known as its boiling point. However hard you heat the liquid, it won't get any hotter. But not everything boils at the same temperature. This is margarine. It boils at around 120 degrees Celsius. Again, the temperature won't get any higher. Liquid nitrogen boils at a much cooler temperature. Even on a tray of ice, it boils and quickly disappears. The opposite of boiling is condensing. This balloon is full of air. Plunge it into liquid nitrogen and firstly the rubber freezes, it becomes crispy, but what's happened to the gas inside? The air has changed from a gas to a liquid. You can see it collecting in the bottom of the balloon. The invisible gas has become a visible liquid. That's what happens when you breathe onto a cold piece of glass. The invisible gaseous water particles in your breath become a visible liquid.
This means that the rate of vaporization is equal to the rate of condensation of the substance in a closed container. Vapor pressure also varies with temperature. The graph shows the effect of temperature on the vapor pressure of water. As the temperature of liquid or solid increases, its vapor pressure also increases. Conversely, vapor pressure decreases as the temperature decreases. At 100 degrees Celsius, the vapor pressure is equal to the atmospheric pressure of 180 m. Boiling occurs at this point, where the vapor of water is equal to the pressure of the atmosphere. There are substances that boil at a lower temperature and some at a higher temperature. These temperatures depend on the vapor pressure exerted by the liquids or solids. Vapor pressure, on the other hand, depends on the intermolecular forces present in the substances. When the intermolecular forces are strong, the vapor pressure is low. As a consequence, boiling will occur at a higher temperature because more energy is needed to break the intermolecular bonds for the substance to change into vapor. Water, for example, exhibits strong H bonds such that vaporization needs more energy to change the liquid to vapor. London dispersion forces predominate in methane, or CH4. These are the weakest forces of attraction among molecules. It needs a little energy to break the bonds such that methane changes to vapor easily. As a consequence, more vapor is released, in which vapor pressure will eventually equal to atmospheric pressure. Boiling then will occur. This explains why water has a higher boiling point than methane. This condition is also true for melting point. The ease with which bond breaks affects the melting point of substances. The greater intermolecular forces there are among molecules, the higher is their melting point. The strength of dispersion forces also depends on the size of the substance or the number of electrons in the substances. The ease with which the electron distribution is distorted explains the amount of dispersion forces that a substance exhibits. Polarizability is the distortion of electron distribution. The greater the polarizability of the electron distribution, the greater is the dispersion forces. When the dispersion forces are high, the boiling and melting points are also high. And let's move to the last one, which is solubility, which is the ability of a substance to dissolve in a given substance, such as solid, liquid, and gas. The amount of any substance dissolved in a solvent or the substance that dissolves another substance depends on the types of interaction among molecules, pressure, and temperature. The rule like dissolves like applies to solubility. This means that the kind of substances being dissolved should exhibit the same properties or should be comparable for them to form solutions. Polarity of molecules is an important factor for substances to dissolve in certain molecules. Highly polar molecules will dissolve substances that have dipoles. The negatively charged particles will be attracted to the positively charged particles of the involved substances. This attraction will subsist in the solutions. Water is considered as a universal solvent because of the ability to dissolve almost everything. Water is highly polar and has the ability to form H-bonds or hydrogen bonds with polar substances. Non-polar substances, on the other hand, will also dissolve non-polar substances. Intermolecular forces such as dispersion forces will prevail to maintain the dissolution of substances. Let's have another activity. Okay, are you all done? Here are the answers. Assessment. Choose the letter of the best answer. Write your answer on a separate sheet of paper. You have 1 minute to accomplish this. Okay, are you all done? Here are the answers. Assignment. That ends our lesson. I hope you have learned a lot and gained new knowledge in this episode. For more inquiries and clarifications, you may call or text your respective teacher in this subject to assist you. It's a great pleasure to be with all of you today. Thank you for taking the time to patiently wait and listen to what I have to say during our lecture. Always follow health protocols and guidelines amidst the COVID-19 pandemic. Remember that perpetual optimism multiplies one's strength. Again, I'm Christine Tiraneses, your teacher on the air, only here at DWND-FM and CMD Cable TV Channel 11, same time every Wednesday, signing off. Keep safe everyone and God bless.